In Chapter 4, we're going to discuss Newton's second law. Newton's second law is going to tell us what happens to an object's motion when the net force isn't zero. If you recall, when we talked about Newton's first law back in Chapter 2, we learned that it's the net force, if we add up all the forces and it equals zero, then the object's motion doesn't change. The object has two possibilities. One, the object is already at rest, in which case it will change. It will not change, it will stay at rest. Or the object's already in motion. If the object's in motion and the net force is zero, it will continue to move in a straight line at a constant speed. There is no force required to keep an object in motion once it's started. Okay, but what if the net force isn't zero? Okay, that brings us to this idea of acceleration. We know that if we say have a hockey puck and it's sitting on ice, I'm going to put it on ice because ice is pretty much low friction. If you take your hockey stick and you hit it, you're going to cause it to accelerate. As long as your stick is in contact with that puck, you're going to accelerate the hockey puck. Once you stop touching it, if there's really no friction, it will continue to move in a straight line at a constant speed. Now, if there's a little bit of friction on the ice, it will continue to move in a straight line and gradually come to a stop because that frictional force will cause it to stop. It makes sense that the harder we hit that puck, the greater that force we apply, the greater that acceleration is going to be, the more we're going to change its motion. Brings us to our first relationship, and that is that acceleration is proportional to the net force. This symbol means that something's directly proportional. When something's directly proportional to the net force, it means that if you apply twice as much force, you're going to get twice as much acceleration. If you apply 10 times as much force, you're going to get 10 times the acceleration. But it's important to remember that it's the net force. So if there's lots of forces acting on something, we need to add up all those forces to find the net force, and that will tell us how things accelerate. Now, one of the forces we often have to deal with when we're looking at net force is friction. Okay. Friction opposes motion. And by opposes, I mean it points in the opposite direction. If you try to push something to the right, the friction force will be pushing to the left. If you try to push the object to the left, the friction force is going to be pushing to the right. If you have something rolling down a ramp and it's moving down the ramp, friction's going to always be pushing up the ramp. On the other hand, if you try to push something up a ramp, you're going to find that friction is down the ramp. So friction's always oppositional. It never works to make motion easier. It always fights you. What causes it? Well, it's caused by kind of two things. They're real closely related. It's caused by surface irregularities. If you look at surfaces on a microscopic level, what you see is things that feel very smooth, even like this whiteboard, at a microscopic level, they're a little bit rough. So if you have two surfaces and they're each a little bit rough, this is the floor, we're just looking at what's going to happen is they're going to catch each other, kind of like Velcro, although not that dramatic. I always think Velcro is the ultimate in friction, okay? The smoother the surface, the less friction. If you don't want your fried egg to stick to your skillet, you put a little oil in the bottom of the skillet, and the oil will fill in all these little surface irregularities and try to create a nice level surface. That's why ice is very smooth. Glass, metal, those things have some friction, but they have much less than rough things like unsanded wood or sandpaper or just a rough concrete garage floor. So the main cause of this friction is these surface irregularities. The other thing you have to kind of think about is everything is made out of atoms, and atoms contain positive and negative charges. So we also get a little bit of electrostatic attraction. They're a little bit attracted to each other, and that causes them to be a little bit sticky as well. But primarily it's that irregular surface. Usually what's going to happen is friction's going to reduce your net force. So if you're pushing this way with 50 newtons, but friction is pushing this way with 10 newtons, what you're going to see when you do your net force is that net force is only going to be 40 newtons. They're not working together, friction's working against you. So friction usually will reduce the overall amount of net force. Now, we categorize friction into two, we'll get this other eraser, broad categories. We talk about friction when the object's at rest, and we call that static friction. But we're also going to talk about friction when the object's in motion. That can be called sliding friction or kinetic friction. Some textbooks use kinetic friction. This textbook mostly just calls it sliding motion to let you know it's moving. Let's think about static friction. Anytime you see the word static in physics, you need to think of something is at rest. Something is stationary. It comes from the same root word as stationary. So in static friction, the object is at rest. So perhaps you've got a dresser in your room. It's full of clothes. It's very, very heavy. And you decide you want to push this dresser across the room. So you've got this great big object, and you push on it with 60 newtons. But it won't budge. Well, in order to remain at rest, we know the net force has to be 0. If you're pushing on that object with 60 newtons and it won't budge, something's pushing back with 60 newtons. And that something that's pushing back is static friction. So this is your push, and this is static friction. And so you push with 60 newtons and you won't move. So you go, okay, well, let me push harder. And you push with 80 newtons and it doesn't move. Well, if it's not moving, the net force still has to be 0. So static friction must be pushing back with 80 newtons. Okay? Static friction can exactly match your push. If I push on this table, I'm going to make up the numbers, but say this is 5 newtons and it doesn't move, I know static friction's 5 newtons. But if I push harder with 10, I know static friction's 10. Now, eventually, you will push hard enough that it will start to move. So there's what we call a maximum value of static friction. If you can push all the way up to 100 newtons before it starts to move, then 100 newtons might be the maximum value of static friction. Okay, so let's say you do that. You push all the way up to 100 newtons, and you notice that the object starts to move. Well, when the object starts to move, you no longer have static friction. We're looking at what we call sliding friction between two surfaces, or some books will call this kinetic. The word kinetic is always associated with something moving. So, in this case, the object is moving. So, if the object's at rest and you're having a frictional force, you know it's static friction. But if it's moving, you know it's sliding friction. Now, what's really interesting is, let's go back to that heavy dresser. That heavy dresser, maybe you finally push with 100 newtons and it starts to move. Sliding friction may only be 70 newtons. Once it starts moving, the friction force actually drops. Normally the maximum value of static friction, which in this case I just picked to be 100, is normally greater than sliding friction. And I'm sure you've had that experience where you tried to push a heavy piece of furniture, a couch or a bed, and once you got it in motion, it was easy enough to keep it in motion. The hard part was getting it started. It takes more force to overcome static friction than it actually will to keep it in motion. So in this case, if you push with 100 and you get it moving and static friction is only 70 newtons, you can see here, you're going to end up with a net force of 30 newtons to the right. It's actually going to accelerate now. It's not only going to move, it's going to start moving faster and faster. Once you get it moving and it's going as fast as you want it to move, you can actually, after it's moving, you can decrease your push to match friction. You can push with 70 newtons. Friction will push at 70 newtons. At that point, the net force is 0, but it's in motion. When something's in motion and the net force is 0, it doesn't stop. It simply moves at a constant speed. So now it will move at a constant speed. Interestingly enough, the speed the object's moving does not affect the frictional force. The frictional force is the same whether or not it's moving at a constant 1 meter per second or whether it's moving at a constant 50 meters per second. There's almost no difference in that force of sliding friction. So it's pretty much a set quantity for those two surfaces. Now, it's really hard to know the only way to figure out the amount of the frictional force between two surfaces is to actually do experiments and measure it. But our common sense says that there'll be a minimal amount of friction between a piece of ice and on a piece of polished metal. There'll be a lot of friction if we're talking about a wooden crate across a rough concrete floor. It just really depends. There's always a lot of friction if one of the things is sandpaper or rubber, any of those things that you think of being either very rough or very sticky. If you want to minimize sliding friction, you want things to be very, very smooth and kind of slippery. Okay, let's make sure I didn't leave out anything. Nope, I think we've covered that. All right, so one of the things that you just want to be aware of when you have two surfaces is that friction may be one of your forces. It may reduce that total force, like here. You're pushing with 100 newtons, but it's accelerating because of a net force of only 30 newtons here. Throughout the class, we're going to be talking about two things fairly often, and those are mass and weight. And in everyday language, we often think of mass being the same thing as weight, but they're not the same thing. In physics, there's a real specific meaning. They're very closely related. If I know mass, I can find weight, or if I know weight, I can find mass. But I need to understand they're not the same thing. Mass is the quantity of matter in an object. It's how much stuff makes that object up. It's also a measure of its inertia. Now you'll remember, the more inertia something has, the harder it is to change its motion, the more it will resist changing its motion. It's that tendency of that object to want to stay at rest if it's at rest. A pickup truck's going to have a lot more mass and therefore a lot more inertia than a toy truck. It's hard to just push a pickup truck. It's easy to push a toy truck because they have different masses and a different amount of inertia. It takes a lot more matter to build a whole full-size pickup truck than it does to make a toy truck. The SI unit, which is, SI units are what they call the International System of Units. Those are the units that scientists have agreed to use. They make our equations stay consistent. So that's why we want to work in meters, seconds. If it's mass, we want to work in kilogram. SI unit is the kilogram, and mass is scalar. Remember, I said you want to pay attention to whether things are vector quantities or scalar quantities. Scalar quantities don't have a direction. Your mass of an object doesn't have a direction. Okay. The other quantity that we talk about is weight. Weight is actually a force. Okay. We don't think of it, but weight is the force of gravity acting on an object. Now, the gravity, that force actually depends on the mass. The more massive something is, the stronger the force that gravity exerts. We're going to learn when we study gravity in chapter, I think it's not till chapter 9, that the strength of the gravitational force depends on mass. So, we know weight is a force. We know all forces are actually vectors. It is a vector, so weight actually has a direction. And it points down. And specifically toward the center of the earth. Now, one of the reasons we might confuse mass and weight is nobody walks around and says, oh, I weigh 120 pounds straight down. We think of weight and mass somewhat interchangeably, but they're not truly the same quantity. Your weight does have a direction. The force of gravity pulls things down. If you trip, you'll fall down, you won't fall up because of gravity. Okay, so you need to know it's definitely a vector. And the SI unit is the Newton. The symbol for a Newton, of course, is a little capital N. We use newtons for all forces, and weight is a force. So you need to remember what the difference is. Mass is the amount of matter, how much stuff does it have, but weight is what's the force of gravity on that particular amount of mass. So, how do we calculate it? Actually, before we calculate it, I want to point out an important piece of information. Your mass, or the mass of any object, is the same everywhere in the universe. If your mass is 50 kilograms, you have a mass of 50 kilograms on Earth, and you have a mass of 50 kilograms on the moon, and you have a mass of 50 kilograms on the planet Mars. If you go to any of those other places, your mass isn't going to change. If I want to throw something horizontally, I'm not working against gravity, I just want to throw it or push it, it takes just as much force to push something on the moon as it takes to push it on Earth, because we're trying to overcome its inertia. So, overcoming inertia is the same no matter where we are in the universe. Okay? However, weight depends on location. The actual formula to figure out weight is that the weight of an object is equal to its mass times the acceleration due to gravity. Weight is equal to mg. Now, if we're on Earth, g is 10 meters per second squared. We've talked about that already. If we need more precision, more accuracy, we can say that we could use 9.8 meters per second squared, but most of the time, 10 meters per second squared is going to be perfectly good. Now, if we happen to be on the moon, g is 1.6 meters per second squared. The acceleration due to gravity on the moon is about 1/6 of what it is here on the Earth. So, if I have a mass of 5 kilograms, and I want to know what it weighs will depend on where it is. If it's on Earth, I'm going to say that its weight is 5 kilograms, that's its mass, times 10 meters per second squared, that's g. If I'm on Earth, this object's going to weigh 50 newtons. You'll notice we get newtons. It's a combination of kilogram meters per second squared. As long as you're using the formula, you can trust that all of this gives us newtons. But if I'm on the moon, that same mass, that's 5 kilograms, only weighs 8 newtons. If you're on Earth, a 5 kilogram mass feels a force of 50 newtons towards the center of the Earth. If you're on the moon, that same object would feel a force of 8 newtons towards the center of the moon. Okay? So, that's the difference between weight and mass. The inertia or the mass of a 5 kilogram object is the same every place in the universe. But it's going to have a greater weight on Earth than it will have on the moon. If we took it to a larger planet like Jupiter, it would actually weigh quite a bit more. So, there's our acceleration due to gravity. If you have to know it for some other planet or location, I would tell it to you. That's your formula for weight. Weight is mass times g, mass times acceleration due to gravity. Okay. It makes sense that mass resists acceleration. Remember, we said mass is a measure of inertia, so if we have more mass, it should be harder to accelerate it. So, let's suppose we have the same force on 3 different masses. Without really knowing much physics, it makes sense that if I put 10 newtons on a small object, think a ping pong ball, I'm going to get a larger acceleration. If I put it on a really heavy ball, like a bowling ball, I'm going to get the smallest acceleration here. And if I pick something in between, if this is a ping pong ball and this is a bowling ball, maybe I pick a baseball. I can see the acceleration here is going to be in the middle. So the larger that mass is, the more it resists acceleration. And what we find is that the acceleration is inversely proportional to the mass. If the mass was up on top, we'd say it was directly proportional. This is inversely proportional. The acceleration is directly proportional to 1 over the mass. So we say this is inversely proportional. Whoa, running out of room. What does that mean? It means if the mass is twice as large, 1 over 2, that's a half, the acceleration is going to be halved. If the mass is 3 times as large, the acceleration will only be 1/3. If the mass was 10 times as large, the acceleration would be 1/10. Which brings us, if we put this with what we talked about earlier, we're going to get Newton's second law. Newton's law. The acceleration is equal to the net force divided by the mass. If I increase this net force, I'm going to increase acceleration. But if I increase this mass, I'm going to decrease acceleration. A lot of times in books, you'll also see it written like this. F net equals mass times acceleration. They're both true. They're just rearranged slightly. If the acceleration is found by using the net force divided by the mass, then it makes sense that if I multiply by m, that the net force is always equal to the mass times the acceleration. So, for example, suppose we have a 40 kilogram block of cement and we apply a force, let's just make sure we know, and the net force acting on it is 200 newtons. If somebody says, well, what's the acceleration? I know the acceleration is equal to the net force, 200 newtons, divided by 40 kilograms. 200 divided by 40 is 5, and I know that if I'm using newtons and kilograms, I'm using those SI units. This comes out in meters per second squared. Let's do a little more complicated example that kind of will tie in all of this together. Suppose I tell you that we have a 1,000 kilogram car and it's accelerating at 6 meters per second squared. It happens to be to the right. I'm going to give you the direction also because I know accelerations should have a direction. So the first question says, what is the net force? Well, I know if I rearrange that formula, I know net force has to be mass times acceleration. So 1,000 kilograms times 6 meters per second squared. My net force is 6,000 newtons. Now, the second part of that question says, if the car's engine is exerting a force of 7,000 newtons, what's the frictional force? So let's think about it. It helps to draw pictures. Here's the car, and a lot of times we just treat it like a point. And I know the car's engine is providing 7,000 newtons of force. It's trying to push this car to the right with 7,000 newtons. But we just found that the net force is 6,000 newtons. Well, if the engine is pushing with 7,000 newtons, but I know that my net force is 6,000 newtons, there must be 1,000 newtons working against me. And that's going to be a much smaller force. That's friction. If I have a push from the engine, of 7,000 newtons to the right, but my net force needs to be 6,000 newtons, then friction must be pushing 1,000 newtons to the left. We just had to kind of fill in the blank of what would make sense. But that's it. So that you end up with a net force of 7,000 minus 1,000 equals 6,000 newtons. Okay. Remember, friction almost always causes that net force to be smaller because most of the time it's working against something else. Now, there are times when friction is the only force. What if you decided you wanted to coast to a stop? Well, you take your foot off the gas. You're not going to step on the brake. You're just going to take this force away. If friction is the only force, then what's the acceleration going to be? If friction's the only force, you're going to have a net force of 1,000 newtons. Remember, acceleration is net force divided by mass. So if my total force, if I step off the gas, I'm not giving it any more gas, I'm just coasting, friction still is going to exert that 1,000 Newton force. As long as the car is moving, that frictional force will be constant. The car has a mass of 1,000 kilograms. Oh, it's going to have an acceleration of 1 meter per second squared. But look at the picture to the left. The car's moving to the right, but the friction force is to the left. Anytime you have velocity and acceleration in opposite directions, you're slowing down. So if the car is moving this way, but the acceleration is that way, you're going to slow down. And you're going to slow down until you stop. Then the frictional force, once it slows down to stop, this moving or sliding friction will go away and there'll just be static friction. It'll just come to a stop. All right. So now that we understand Newton's second law, it's written two ways, this way, or we can write it this way. We're ready to move on to the idea of free fall. No, don't like that one, it's dirty. We talked about free fall in chapter 3. We just want to talk about it a little bit more. When an object's in free fall, the acceleration is g. When something's in free fall, we can totally ignore air resistance or any other type of frictional force. It's simply falling because of the force due to gravity. Well, let's think about the forces. When something's in free fall, the force that acts on it is its weight. So, suppose I have a 2 kilogram object in free fall, the force that's acting on it, the only force, is its weight, which is mg, so 2 kilograms times 10 meters per second squared is 20 newtons. So, if your 2 kilogram mass is in free fall, it has a force acting on it that's 20 newtons. If a 1 kilogram object is in free fall, the net force acting on it is also its weight. A 1 kilogram object in free fall feels a force of 10 newtons. Okay, this is where some kids get confused. They go, oh my goodness, Miss Hughes, this one's got twice as much force. Shouldn't it have a larger acceleration? It's got a bigger force. But you have to go back and think to Newton's second law. Newton's second law says acceleration is net force divided by mass. If the net force is 20 newtons and your mass is 2 kilograms, your acceleration is 10 meters per second squared. If your net force acting on you is 10 newtons, then you still have an acceleration. So, yes, it is true that the force on a heavier mass is greater. The more massive an object is, the more it weighs, the more the force of gravity is going to act on it. But the thing you have to remember is, even though the force is greater, the inertia is also greater. If you have twice the weight, you also have twice the mass. So there is a larger force when more massive things are falling, but there's also larger inertia when more massive things are falling. So they will feel different forces. A 2 kilogram mass feels a different force than a 1 kilogram mass. And those are much smaller than the force felt by a 100 kilogram mass. However, all of those will feel the same acceleration as if they're in free fall. As long as we can ignore air resistance, or what they call, another word for air resistance is air drag or fluid friction. As long as we can ignore that, and the only force acting is the force of gravity, all objects will accelerate at the same rate, which is 10 meters per second squared, or 10 meters per second each second. That's what Galileo discovered when he was dropping those balls off the top of the Leaning Tower of Pisa. Now, there are times when we cannot ignore air resistance, where it does make a difference. What if we have a situation that is non-free fall? Well, if I'm in a state that's not free fall, the acceleration is less than g. And the reason the acceleration is going to be less than g is it means this is a situation where it's not possible to ignore air resistance. And there's a lot of real-life cases where it's not possible. If you drop a feather, unless you drop it in a vacuum, if you drop a feather in a vacuum, there's no air, it accelerates down at 10 meters per second squared. However, if you drop it in the air resistance matters. If you are jump out of an airplane, well, if you don't have a parachute and you ball up into a tight little ball, you're going to pretty much be in free fall. But if you open a big parachute that has a large surface area, well, the whole premise of a parachute is that it makes that air resistance or that drag force, or that fluid friction, all those words mean the same thing, become very, very important. The net force on you won't be your weight anymore. What's going to happen is, when you're not in free fall, you're going to have two forces. Here's something. The object still weighs as much. The weight is going to be pulling it down. But the air drag is going to be pushing it back up, so that the net force is actually smaller, and you will accelerate at some value less than g. Now, what does that depend on? Well, the air drag basically depends on two things. It depends on the surface area. I demonstrated earlier, if we drop a sheet of paper it takes a while to come down. But if I were, and I may have already thrown it away, if I wad that sheet of paper up into just a paper ball, and I make that surface area much, much smaller, it has much, much less air drag, and it will drop and accelerate pretty much the same speed as a marker, okay? The whole principle of a parachute is that you get this great big area over your head. You greatly increase your surface area. And by greatly increasing your surface area, you increase this air drag. And that slows you down. Okay? The other thing that affects air drag is how fast you're falling. So larger surface area increases your air drag. Faster speeds increase air drag. I should probably have said that. Look, large surface area increases air drag. I want to make sure you know how the surface area affects it. So if I have a really large surface, I'm going to increase it. But if the object falls as it gains speed, the friction force increases. That's different than with sliding friction. When we talked about sliding friction when you push something across the floor does not depend on how fast you push it. It stays the same. If the friction force is 25 newtons, it's 25 newtons whether you're pushing it at 1 meter per second or whether you're pushing it at 30 meters per second. But when things fall through the air or water also exhibits fluid friction, quite a bit more than air. If you've ever tried to walk across a swimming pool, you know that it's much harder to walk through a swimming pool than it is to walk through air, and that's because of fluid friction. But the faster you're moving, the more air drag you're going to have, okay? So eventually, when things fall, you'll reach if you go fast enough, you reach terminal velocity. At terminal velocity, these two are equal. At the terminal velocity, air drag equals weight. Well, now what does that mean? If the air drag is equal to the weight, the net force will equal 0, and you're no longer accelerating. So if you forget your parachute and you jump out of the plane, you're going to accelerate at 10 meters per second squared. But if you'll spread yourself out, stick out your arms and legs, try to be as big as you can actually increase your surface area and you'll get some more air drag. Eventually, the air drag will equal your weight and you'll stop accelerating and you'll fall at a constant speed. The terminal velocity is a constant speed because the net forces on you are 0. Now, it is true that the more something weighs, the longer it takes to reach its terminal velocity. So, heavier objects have higher terminal velocities. So let's suppose that you have a husband and a wife. They have identical parachutes. So the air drag on the parachutes is going to be the same for both of them. But if he weighs more than she does, if she's a tiny little 120 pounds and he's a big 220 pounds, it will take him longer to reach terminal velocity. And when he does reach it, it's going to be a much faster speed. So he will definitely hit the ground first. Okay, so that's a little bit different. Remember we said when we can ignore air resistance, everything falls at the same rate. But if we cannot ignore air resistance, things will fall at different rates. And if they have the identical shape where surface area is not a factor, if air resistance is a factor, then heavier objects do fall faster than light objects. We all know that if I have a paper clip and a feather that have the exact same mass, but if I drop them, that paper clip's going to reach the ground first. It's going to have a greater terminal velocity. Okay, I think that's everything out of chapter 4. If you work through the homework and you come up with questions or you need clarification, shoot me an email and ask, okay? And we've got one more chapter to go over in this unit, and that's going to be chapter 5. That's going to be Newton's third law.